Problem number 14 from Hall and Knight Higher Algebra, Chapter 1 Ratios. If a square plus b square plus c square multiplied by x square plus y square plus z square. Now, if this is equal to ax plus by plus cz squared, then we have to show that x is to a is equal to y is to b is equal to z is to c. So what we have to prove essentially is x over a is equal to y over b is equal to z over c. This is what we have to prove. X is to a is equal to y is to b is equal to z is to c. Okay. So for solving this problem, let us first consider the left hand side. That is, we want to consider this here. We simply multiply this. Okay. So if you multiply this, what we get is a square times x square. So you get, so let me write it clearly that this is LHS. Okay, this is LHS, left hand side. A square x square. So you get a square x square plus a square y square plus a square z square plus b square x square plus b square y square plus b square z square plus c square x square plus c square y square plus c square z square. This is our LHS. Now we have been given, we will now expand this. So let me use a different color so that you can see. I will use a different color. Let us say we'll use this color. So RHS is equal to, you can simply apply the formula of a plus b plus c square. So this will be equal to, we have been given that RHS is equal to HS, LHS is equal to RHS. So this becomes a square x square plus b square y square plus c square z square plus 2 times ax by plus 2 times by cz plus 2 times cz ax. Okay. Now we see that a square x square cancels out because they are present on both the left hand side and right hand side. B square y square also cancels out. C square z square also cancels out. Okay. So now we will write the remaining term. Okay. So what we have is, we have a square y square a square y square plus a square z square or let me write it different way. We have a square y square, so we see that which of these terms has a y. We can already see that 2ax by has term a y. Okay, and besides a y, it also has term bx. So can we find b square x square over this side? Yes, we can. So we will write a square y square plus b square x square. I am just writing it in different order. That is, I am taking a square y square here and b square x square from here. There is a reason I am doing this, and you will soon see why. This 2ax by can be written as minus 2 times ay times bx plus, then we have a square z square, a square z square. We can see that we have a z term over here. Besides a z term, we have cx term, so we will find c square x square, which is over here, plus c square x square minus 2 times, we can write this as a z c x plus, we have already used this term, b square z square plus c square y square minus 2 times bz cy. Now this is equal to 0 because we have taken all of these terms and subtracted it from the terms over here. So this will be equal to 0. Okay. Now the first expression, that is the first row, can be written as ay minus bx square. The second term can be written as az minus cx square, and the last row can be written as bz minus cy square is equal to 0. Now you see that we have 3 square terms. So what we know is that either each of this term is going to be positive because it is a square, or it can be 0. So how to add 3 positive numbers that you get 0? There is only one way you can add 3 positive numbers to get 0, and that is if each of these terms are themselves 0. That is, if this term is equal to 0, this term is equal to 0, and this term is equal to 0, only then we can get 0, because none of these terms can be negative. They can either be positive or they can be 0. And if you add positive terms which are not 0, you will never get 0 here. So there is only one solution to this problem. So what it implies is that ay is equal to bx, az is equal to cx, and bz is equal to cy. Now let us see what we had to prove. We have to prove x over a is equal to y over b is equal to z over c. We can find x over a from here. This implies that x over a is equal to y over b. We have taken b this side in the denominator and a this side in the denominator. From this over here we get x over a is equal to z over c. So we already know from these two equations that from these two equations itself we can say that x over a is equal to y over b is equal to z over c, and we are done. We have already proven what we wanted to prove. But even if you use this equation also, what you will get is you'll get y over b is equal to z over c, which is anyway we have already shown from these two equations. So this equation is redundant, but in any case you can take any two equations and you will get this result. And this is what we had to prove.